In this video, I want to use the manipulatives to help represent the fraction division. We want to, again, develop this conceptual understanding and understand what's happening when we talk about division, how the manipulatives then show that division, and then how that helps to develop that standard algorithm or that procedure for dividing that many of us are familiar with, but we don't understand why it works. We know it works every time. It's pretty easy, right? Flip and multiply, but why does that work and where does that come from and how does that make sense? So as with all things, we always want to start out with a context, right? So when we think about dividing whole numbers, we think about division as how many groups or how many in each group, right? We have the measurement division as how many groups, or we talk about partitive division, which is how many in each group, right? I'm going to take something and I'm going to cut it into pieces. So when we're thinking about division of fractions, both interpretations can be utilized with fractions as well. Let's take this example here. We have 1.5 cups of sugar. It takes 1/3 of a cup to make one batch of cookies. How many batches of cookies can you make? Pause the video for a second. So which type of division is this? Is this how many in each group, right? Is that what the question asking is, how many cups in each batch? Or do we know that information? We know that there's 1/3 cup of sugar in one batch of brownies. So now we want to know how many groups, how many batches can we make? So this is that measurement division, how many groups. So let's now think about how would we represent this? We have 1.5 cups of sugar. And now we want to divide it by 1/3 cup of sugar, right? How many 1/3s can fit into 1.5, right? How many 1/3 cups can fit into 1.5 cups? And this is where, if you watched closely the Graham Fletcher videos, he talks about this goes into, right? If you've ever heard that, 5 goes into 10 2 times, right? And that's how a couple people think about division. You can think of this goes into language or fits into, but really we want to show that. So here we go. So let's take our area model. We love our fraction circles, the pizzas. That's one we're very comfortable with. So that's why I figured we'd start here. So let's think. We have 1.5. Make them with your fraction circles. And now how many 1/3 pieces can fit into our model here? 1, 2, turn this around, 3, oh, and so here we have 3 full 1/3 pieces are fitting right here into our fractions. I'm going to assume that you can see how that lines up. And now we see again how many 1/3s fit into this 1.5. Well, we have 3 full 1/3s in the one, right? How many 1/3s goes into, or how many 1/3s are in one whole? 3 1/3s are in whole. We can also see that an entire 1/3 fits into this 1/2. But now how much is this piece? Let me see if I can move it. So how much is this right here? How much of that 1/3, again, notice the language changes, no longer how many fit in, but with fractions, we change our language to how much fits in. So how much is that? So if we and again, pause the video, use your fraction circles and see what size fits into there. And I didn't finish writing this out. So how much is this? And it's not even just how much, but how much of the 1/3? Because if you guessed, or if you found that it was 1/6, right? That size right there is 1/6 of the whole, but how much is that 1/6 of the third? So 1/6 of the third How many 1/6 pieces fit right here in this 1/3 piece? That's half. So this is how we get 4.5 times 1/3, right? 4.5 times 1/3, right? 1/3 pieces times 4.5 gives us our 1.5. And now you can also check this. Do the flip and multiply. 1.5 we can rewrite as 3/2. We're going to multiply that by, right, flip the 1/3, multiply that by 3/1, or 3. And what's that? Multiply across 9/2, and 9/2 is the same as 4.5. Sorry, my writing is not great here. And we can literally see that with the fraction pieces. 4 whole 1/3, right? 4 1/3 pieces fit into the 1/2, and then how much of this 1/3 is left? Half of the 1/3. So we have 1, 2, 3, 4, right? 1/3 fits in 1 time, 2 times, 3 times, 4 times, and a half of a time. This is the language we want to start using with this division, because I know this is way too easy to just tell people to do it. It works every time, boom. But we want to build to that. We don't want to start there. That's going to be the last thing we want them to start recognizing that pattern, to pick up on that. So here we just saw it once. I just wanted to show you this connection up front, because I know you'd be wondering, so start with that, or start with this idea of counting how many times the one fraction, right, the divisor, fits into the dividend. And then your quotient is, again, how many times this 1/3 went into this 1.5. So now let's look at the area model again, but with rectangles or strips. Here we can see that we have 1.5, and again, we're going to see how much does this 1/3 fit into this whole and then this half. I'm going to switch to this screen so that way I can show you the overlay, right? We can see this 1/3 fits into a whole 1, 2, 3 times, but then it fits onto the half a whole time, and then there's still extra here. What is this space? And so if we bring that down here, we can see that the third fits into the whole again 3 times. Let me see if I can get the pen working here, right? It can fit in 1 time, 2 times, 3 times, right? Because we can divide this into thirds. We see it goes into a 4th time, but then what's this? Right? How much, as we just said, how much of the 1/2 is that space? Or sorry, of the 1/3 is that space? And there's my little slip. We can see that bit is exactly 1/2 of the third. So that's why the 1/3 fits into a whole and a half, 1.5, 1, 2, 3, 4.5 times. Now let's go back to now let's try it with the set model. How can we see this same division idea with the set model? So let's choose our sets and define them accordingly. So one whole, we can make a set of 6. And think to yourself, so why do you think we chose 6? Why didn't we choose 8? What's special about 6, especially with regards to this idea of halves and thirds? I didn't make it as the array, but again, those same ideas from defining fractions, creating equivalent fractions, and then adding and subtracting fractions, right? Defining your whole so that we can see both fractions is really important, right? We can see halves and thirds in a whole that's defined as 6 pieces. So if one whole is 6, then what is, I think this will be, how do we show 1.5? right? 6, and then 3 more would be 1 whole and a half. And then what would be 1/3? 2 pieces would be 1/3. So again, we see 1/3 fits in 1 time, 2 times, 3 times, 4 times, and a half of a time. Right? We see 1/3 fits in once, twice, 3 times, 4 times, and then this one counter compared to the 1/3, right? That's half of a 1/3, which again, it would be 1/6 of the whole, but we're not looking at comparing it to the whole, we're looking at comparing it to the divisor, to the 1/3. So lastly, let's check out the length, the linear model. So again, we can define our whole on our number line, and then 1 1/2 would be a whole and a half. And now how many 1/3s fit in? 1, 2, 3 thirds fit into a whole, another third fits into the half, and then we want to know again, what's that little piece? So we can compare this to how much of the third it takes up, and now we've seen it more than once. We've seen how it creates, how it connects to flipping and multiplying, the procedure for dividing fractions. And so I encourage you, try this with the Cuisenaire rods. Does it still work? How would you define the Cuisenaire rods? So that way we can see this. Create another context. And let's try that division. And what I want to leave you with is now 3, well, here is our original question, but what about these other 2 questions here? You have 1 1/2 cups of sugar. It takes 1 cup to make 1 batch of cookies. How many cups of sugar are left after you make 1 batch? Is that a division problem? You have 1 1/2 cups of sugar. It takes 1/3 cup to make 1 batch of cookies. How many more batches of cookies could be made with the sugar that's left over after you made the first one? So again, I want you to be very careful about the language that we use when we're talking about fractions, because the word choice matters. So to end here, I'm going to use the Cuisenaire rods, and I'll keep the labels on. The dark green is length 6. So if we wanted to go back to that same problem of 1 1/2, we would have a whole, not the 4, and a half, right? That's 1 1/2. And now we want to think about, well, what is 1/3, right? 1/3 of the whole would be our little red, the length 2. So now we want to see how many 2's fit into the whole, how many little red ones fit into the dark green one. And I'll turn off the labels for a minute. So we can see 1, 2, 3 little red ones fit in the whole. A 4th little red one now fits into the half. And then how much of this little red one right here fits into this, right? This is our 1 1/2. We have 1, 2, 3, 4 1/2 little red ones that fit into the green.